Hello. Recently I did a video where I talked about solving this certain math problem, this certain physics problem with different levels of uh, programming languages. And one that I wanted to include that I left out was assembly language. And so in this video, I'm going to do the same math problem that I solved before, but I'm going to compare one of the languages that I did last time with solving the same problem in assembly language. And in this one, the thing that's really fascinating here, so as a controls engineer, is very interesting for me to see the comparison of the programming between what's akin to assembly code on a PLC versus assembly code on the ARM processor, which is used in maybe some PCs, telephones, or the Raspberry Pi. Um, so yeah, this is so let me first kind of compare real quick the architecture between the two, and then very briefly hit the algorithm that I use for the PLC, and then go more depth in the algorithm for assembly code. So this, all right, so if we take our PC, our ARM processor, we have these registers that are shown right here, which this tool is amazing. I really like this training tool, which you can see the website right there. Um, so yeah, this uh, R0 through R6 are general purpose, and then there's a whole ton of like specific registers. And then there's the RAM. And so if I were just kind of make a quick little reference here, so on the ARM processor, we have 6 general purpose registers, a bunch of specific registers, and then I'll do a box here for RAM. Okay, so this is kind of the memory layout on the uh, ARM processor. And the layout on the PLC is we have 2 accumulators. So I'll try to keep the, and this is a Siemens PLC, and that's actually a 300 or 400 PLC because it changes quite a bit from model to model. But we have 2 accumulators. We have several other short-term, not short-term, speedy access memory places. So those would be we have 2 registers. We have 2 places for the data block references. And there's going to be counter values and timer values. And then we have a whole ton of what's just really called memory, honestly. And for the purpose of what I'm about to show in a minute, we're calling them memory words. And a word means something different on a PLC than what it does on a ARM processor. The length is different, but that's not important for our purpose here. So that's what we're going to do. And in this one, basically, on the PLC, you have your code, which we could say this is your code, and then the other one we could say this is your code. Your code is going to take and interact with these quick access places, and then let's use a different color here, maybe use white. The code's going to go to the quick access places. I'm ignoring these for right now. They exist, but I'm not going to use them. Same over here. I'm not going to use these. The program will actually use these a couple times, but I'm not really going to pay attention to them. So the program will access these quick memory places, and then the quick memory place will access the slower memory, and then vice versa. It goes the other direction too. And that's the same here. The program will access these registers. The registers access the RAM, and vice versa. So that's enough about hardware architecture. Um, so first I'm going to start, as I said, and go very quickly over the PLC code. And I like to do it all with comments, but I want to keep this shorter. And I don't have comments for my assembly code because, well, the emulator doesn't like the comments, and I didn't feel like going through and deleting them. I have the comments up here, but this code doesn't work. The code that works, I didn't add the comments. So um, just to briefly go over this, it's relatively short. All we do is we take our measured height. Oh, I didn't explain what the algorithm is actually going to do. So due to the magic of calculus, uh, and the basic laws of physics, Newton's laws of physics. If you have, um, if you take an object and drop it from a window and have really accurate measuring devices, then theoretically you can use that to calculate little g, which would be the gravitational constant for the Earth, which should be 9.8 something something something. And basically what happens is, for the purpose of my algorithm here, I want to imagine if you took, say, a ball and you dropped it off a certain height, maybe out of a window, and you measured the time it took to fall and hit the ground. And I want to say that you do that 3 times just to get a more accurate measurement. You only have to do it once, but 3 times, and then take the average to get a more accurate value for your time value. And then if you just take 2, multiply it by the height that the window that you dropped it from, which in this case was the height of the window, and then divide that by the average time value squared. That will give you a value for g. And so that's what we're going to do. The values that I picked, because I wanted to keep everything without decimals, are very convoluted and not convoluted, very contrived. And so what we have here is we have 20 for the height that we dropped from. The 3 values are 1, 2, and 3, which means that as we work through this, so we're going to take 2 times the height. 2 times 20 is 40. We're going to divide by, we need to calculate the average time value. So 1 plus 2 plus 3 is 6. Divided by the number of entries, 6 divided by 3 is 2. And we're going to take that time value and square it. 2 squared is 4. So 40 that was on the top divided by 4 on the bottom gives us 10, which is our rough estimate for G, which is not super far off from 9.8 depending on your perspective. So that's what's going on in both examples here. So for the first one, running through the algorithm, maybe I can get this picture right here. This might help a little bit to reference this. So we're going to take and we're going to load 20 into accumulator 1. Then we're going to transfer it to this memory word location, memory word 100. These kind of have to be pre-planned, and I have kind of a chart here for what each of the memory words is. 100 is the height, 110 is the first time value, 120 is the second time value, 130 is the third time value, 150 is going to be a container that I'm going to use for the average time, 160 is going to be the container I use for 2 times age, 170 is the container I use for the average time squared, and then 200 will be the container where I put the output, the result. And in both cases, for the ARM processor and for the PLC, ideally you would actually have these interact with hardware, but you know, I wanted to focus on the algorithm, so I didn't do that in either case. But yeah, so we're going to load 20 into the accumulator, then transfer it to our specific place in memory. Then we're going to load 1 into the accumulator, transfer that to our place in memory. Same for 2, same for 3. Now we have our height and our 3 time values, everything that we measured. Then we're going to calculate the average of the time values. So in this one, we need to know that when we load, so we're loading the value that we put in memory word 100, which is 1, our first time value. So we load 1 into accumulator 1, and then every time you load, it actually pushes what was in accumulator 1 to accumulator 2. So we're putting 1 into accumulator 1. Then the next step, we're going to move the next value, which was a 2. So we move 2 in accumulator 1. It puts 1 in accumulator 2. It pushes this over. And then when we add them, it puts the result in accumulator 1. So we add these 2 and put the result in accumulator 1, which is 3. And it leaves the 1 over here because it's not important right now. Then we're going to load 3. We're going to load our third time value, which was 3, which pushes this 3 over here. Then we add load, that was this one, load this one. Then we add them. When we add them, we get 6 here and 3 here. Then we're going to load 3. The reason to do that is this 3 here represents the number of entries, and in both cases I hard-coded it, but it would obviously be better to use a counter in both cases, but I didn't do that, I just hard-coded it. So, and then that moves the 6 over here. Then the divide instruction divides the 6 by the 3 and puts the result here. So we have 2, and then we have 6. And then we're transferring that into memory word 150. So we're going to put that into the memory that represents the average time value. Then we're going to load 2. So we get 2 in accumulator 1, 2 in accumulator 2 because it shifts over. And then I lost my place. Load this one. Then we're loading memory word 100, which was, what was memory word 120? That's the height. So we get 20. Then the 2 that was in accumulator 1 goes to accumulator 2. We multiply them. We get 40. This 2 stays. Then we're going to transfer into memory. Then we're going to load 150 twice, which 150 was, that's going to be our average time value, which I just remember that, or I could look over at my chart that I made here. Average time, because we need to square, that's why I knew, we need to square the average time. So we load the average time, so it's going to put a 2 here, a 2 here, because we load it and then we load it again. And then we're going to multiply them together, which will give us 4, which is time squared. And then we're going to transfer that into a memory location. And then we're going to load 160 and then 170. 160 was, it's easier to look over here. So we're going to load 2 times h and then t squared. So we're going to load 40 and then 4. So first we load 40. It pushes the 4 over here. Then we load 4. It puts the 4 here and it pushes this 40 over here. And now when we do our divide, it takes 40 divided by 4 and it gives us 10. And then the last step here, transfer to memory word 200, is to move our solution into the memory location that we are concerned with in our long-term storage memory. So we have 10. Okay, so that's the algorithm on the PLC and what is done on the PLC, and pretty much how these 2 accumulators, accumulator 1 and accumulator 2, interact with the code and then with the long-term storage memory. For the ARM architecture, for the ARM processor, we're going to just look at the code here, which I didn't copy and paste yet. So my code is down here. Okay. And hopefully everything was correct. So it should be correct. I think I have to get rid of this part because I didn't make that correct for a comment. So, or not a comment, like a tag. It'll take tags, but the emulator won't take comments. So I had to. That's why there's no comments. Otherwise, I'd have to go through and delete every single comment, and it just takes forever when I comment a lot. So in this code, there's a few added things. So the first part is these right here represent specific locations in memory, which if I pull this out so you can see it, this memory address that is 0 in hex is this one right here. And then this next memory address is 4. The next one is 8. And then the next one is 12, which is C in hexadecimal, and so on. And that's what I'm doing here, is just assigning names to the first, what are 1, 2, 3, 4, 5, 6, 7. The first 7 memory addresses here. 1, 2, 3, 4, 5, 6, 7. I'm assigning names, so that makes it easier later on during the program. I can reference them by name instead of by address. So that's what this first part is. This next part, global start and start, basically just allows you to have the assembly code run. It's necessary so that it can run. It's the place where the code starts. This right here is completely just for testing purposes, so that when I run the code repeatedly, it changes the registers 0 through 6 to values 255, so that way I can just watch them change as I run it multiple times. Kind of cleans out the memory for me, just for testing and debugging. Then the next part here, we're gonna load the values. So we load our height, and our 3 measured time values, very comparable to what we did in the STL code, the statement list. I don't know if I mentioned that earlier. The programming language that I was using for the PLC was called STL, which stands for statement list. And next thing we're going to do then is we're going to take our, what did I calculate the average? We calculate the total of the time, then we divide the time by 3 to give us the average. This is the division right here. And then we multiply the height times 2 to give us that 2h, the numerator of our fraction that we want. Then we square the average time value to give us the denominator, the t squared. Then we divide those two to get the final result, and we store the final result in a specific location. And now to go through it in more detail, we'll actually run it and step through it. Successful. Okay, so you can see that this basically looks the same as what I had before. I can move that over a little bit. This is what I want to get rid of right here. Yeah, that's better. Okay, so the first line here after start, we're going to move the value 255 in decimal. I have everything in decimal. I want this in decimal too, actually. We're going to move 255 into register 0. So when I hit either step into or F2, you'll see that happen. And the next one moves 255 into register 1, and so on down the list. Register 6. Okay. Then the next one here is going to load a 0 into register 0. And what I pretty consistently chose to use register 0 for was the addresses, the address references to reference the address location in our RAM. So when I do this, it's going to put the RAM address 0 into register 0. Then we're going to load the decimal value 20 into register 1. Then we're going to store the value that is in register 1, which is 20, into the address that is pointed at by register 0. That's what the brackets here tell you. And that address is 0, which 0 is the first one here. So this long thing should change to a 20, which it did. And so on. Actually, I'm going to skip through the rest because it's basically repeat the same process to load the 3 time values. So that's time 1 is 1, time 2 should be 2, time 3 should be 3. Okay. What's next is we calculate the total time. So we're going to add registers 2 and registers 3, which because of what I did before, those didn't clean out, so those are actually still the from the previous loading step. That's where I ended up putting this was our first measure time value and our second measure time value. We're going to add them and put that into register 5. So register 5 should change into 1 plus 2, which is 3. And then the same thing, adding the value, the sum that we just had, plus the sum that we just had, which is 5, or register 5, plus the remaining time value that I didn't include, which was register 4, will give us a 6 and put it in register 6. Then we're going to take and store our total time and put it in the address that R0 points to, which I think I must have skipped that. I did. I skipped that. We loaded into register 0 the pointer that the total time points at, which is 12. So that'll be we have 0, 4, 8. No, wait. Yeah, 0, 4, 8. That should be 12. Is that 12? Let's see. I'm going to skip here. Okay, yeah, because it changed to 20. I think I got lost in my following of it, but anyway, so now we're taking register 6, which was 6, and we're loading into R0 points at 20, which, sorry, that's 20. Yeah, that's decimal, so 20, it should be 0, 2, 4, 0, 4, 8, 12, 16, 20. So right here should change to a 20, or a 6, because it pulled the value from register 6 into the 20 RAM address. Then we're going to do, we're going to move 20 into R0, which is actually already there. We didn't need to do that, but I did it anyway. Then we're going to load the register, and we're going to load the value that registers the value, how to say this? So register 0 has a number in it that points to a RAM location, and that number that is in the RAM location is what we're going to load into register 3. So if I look, register 0 points to 20. 20 was this one that has a 6. So we're going to load that value 6 into register 3. So when I push step into register 3, it should change to a 6, which it did. And then we're going to load the decimal value 3 into register 4, which it was already there actually. And we're going to load a 0 into register 5. Then we do this loop, and this is the division. So this here was to set up the division, some things for the setup to get the numbers in the right place. And then this actually is the division. So the way to do division on the, well, a way to do division on the ARM processor is to actually do subtraction and count the number of times you subtract until you get to either 0 or a negative number, because there is no hard-coded division opcode. So that's what's going on here. And to make it shorter, I'm not going to sit there and spell out every single step, I suppose, but you can watch it happen. We put a 1 into R5. I think that updated the counter, the PC counter. Anyway, so when we get done with this, the key is when we get done, so this BPL tells us that we're going to break out of the loop when we hit either 0 or a negative number, when we hit a number that's not a positive number. And when we do that, we add here, this part gives us the remainder, which the remainder is 0. I picked those numbers on purpose so that there would be no remainder. And then after that we do subtract here. This is because the way that it was set up above, it actually gives you one more than the number, and so we subtract to get to the actual number that we want. And so when we're done right here, R5 will have our division answer, and then we're going to move, we're going to load this average time pointer to, I think pointer is the right word, into register 0. Then we're going to move, do this, that is the same as this. That's telling you that average time is 16, I believe. And then we're going to store from the value that's in register 5, which was the result of our division, into the value that's being pointed to by register 0, which will basically means it goes into average time. And so we know that the average time in this case is supposed to end up being 2. So you'll see that when this breaks out, it puts a 3 into R5, and then that's why it subtracts 1 to make it a 2. So that's what we'll see here. So now we broke out of it, and you'll see that there's a 3 in R5. We're about to subtract 1 from it. That puts our 2. And then now, as I said, I kind of went over this already. So we moved our pointer into register 0. Then we moved our value into the value being pointed at. And this is 16 because we go 0, 4, 8, 12, 16. Then we multiply the height times 2. So we're going to move a value 0 into register 0 because that is where I have the height stored, which was mentioned above, which is actually right here. You can see it's pointing to the height here and then here. It kind of does it in 2 steps. I wrote it out in 1 on the previous line, so line 63 you'll see is just 1 line, but here it breaks it out, and so it pulls the value that is in height, and it actually does that on a separate line. So it pulls the value from height, and then it puts that height value in here, is what it's doing anyway. So yeah, we're going to move that. Then we're going to load the register. We're going to load the value that this R0 is pointing at, and it is pointing at the RAM. Should still be pointing at this one. So 20, and that's going to load the 20 into R1, which happens to already be there. That's kind of a coincidence. I guess I didn't need that. I don't remember when I put that there. Then we're going to move the number 2 into R2. Then we're going to multiply R1 times R2 and store the result in R3. So that's going to be 20 times 2. So in R3 we'll see 40. And if you remember from the whole practice thing and everything, that's supposed to be 2 times h. That's our numerator of our fraction. Next step, we're going to move into R0, which again, I consistently kept that as the pointer. You don't have to do that, and I'm pretty sure you don't have to do that, but I chose to do that to make my life easier, so that I could remember where my pointer was to the RAM. It's just the way that I chose to do it. So um, we're loading the average time right now, and the average time is stored in 16. 0, 4, 8, 12, 16. So it's this 2. We're going to take that 2. Sorry, this is actually 16. Then in the next line, which I'm not at yet, we're going to take the 2 and put it in R4. So when I push this twice, you'll see that R4 changed to 2. And then now we're going to multiply. And in this case, we're just multiplying the value that's in R4 times itself and then storing the result in R4. So this is going to change into 2 squared, which is 4. And then now we need to divide. This is the final step. We need to divide our numerator, which was 40, by our denominator, which was 4, which will give us our result, which is 10. And I guess this time I'll go through the loop maybe once explaining it, but I have to loop through it 10 times, so I'll go pretty fast once I get it going through it once. But the first time here, we move 0 into R5. This is just to make sure, because we're going to use R5 as like a counter, how to say that, I think is a counter for the remainder. I actually have to look and see. I think it's, yeah, we're using that as the counter for how many times. It's basically the solution to the division. It's how many times we've done the subtraction is going in R5, so we need that to start at 0. So that's what's going on right here. And then we entered our loop, because down here at this line it says loop 2. It's going to bring us back up to here. So the first thing that we do is we take R4. It's going to be the other way. We take what's in R3, which is 40, and we subtract what's in R4, which is 4, and then we restore the result in R3. So it's going to be 40 minus 4 is 36. See that? And then the next, so we did one subtraction. So now that we did one subtraction, we need to have the number 1 in R5, our counter. And so that's what this is going to do. It's going to move 1. Well, this is actually an add. So we take what's in R5, which in this case is 0. We add 1 to it, and then we move this result into R5. Okay, and then we hit this BPL, which tells us to go back. I forget what the B stands for, but anyway, it's B plus. The PL stands for plus. I don't remember what the B stands for, but it's telling us to jump back as long as we're not at 0 or a negative number. So, and since it must be looking, where is it? How does it know where to look? You know, I actually don't remember that, but it's got to be looking at the R3. Anyway, I don't remember off the top of my head where it looks at, but so because we're not there yet, it's going to go back to loop 2. And you'll see now we're back at the subtraction line. You know, it actually might be, you know, my bad. We're not just plain subtraction, we're subtraction with status flags. So it's actually watching this here, so that when the result of the subtraction is negative, I think it has to be negative. Positive and 0 are both okay. I had that mistaken earlier. So this, you'll see this N set down here for CPSR register when the result of the subtraction gives a negative number. And that's why at the end we need to add 1, because we actually are supposed to stop the loop when we hit 0, but it stops when we hit negative. So because of that, we need to add 1 back to it, because it means we went one loop too many, if that made sense. And so now I'll just continue to ram through these. So you see there's a 1 in R5, so we have 36 and 1. And by the end of the next one, we should get 32 and 2, 28 and 3, 24 and 4, 5, 6, 7, 8, 9, okay, 10, and we're at 0, but it's going to go through again because it's not negative yet. It is 0, right there's a Z, but it's not negative. So now it's negative, and now the negative flag is set, but we're still inside the loop, so we still have to add 1 to it. So it's 11. Now we're at the break, oh break, I think B stands for break. Now we're at the break point again, and now we have a negative flag set. So when we hit it, it'll move to the next line. And the next line it's going to add, so it's going to do R3 and R4, R3 and R4, which I believe this should be, this must be -4. It doesn't look right because I have it, it should be signed, I guess. Yeah, so -4 and 4. It's going to add those, and then it's going to store the result in R6. So R6 is the remainder, which the remainder is 0. So the next line then is going to take and subtract 1. See, this time there is no S. This time we're not concerned with flags. We're just playing subtraction without paying attention to the flags on the CPSR register. So when we take the value in R5, which is 11, we subtract 1, which will give us 10. Now this is our result. So we're going to move, first we have to move the result pointer, I guess. I feel like that may not be the exact right word, but we're going to move the result pointer into R0. The result pointer here is 20 in hexadecimal, which is 32 in decimal. So we're going to move 32 into R0, and you'll see that. And 32 is going to be 0, 4, 8, 12, 16, 20, 24, 28, 32. It should be right below the 2 there if we count it right. So we have, now we're going to move the value from R5, which is 10, into the address being pointed at by R0. So there it is, 10, and that's the solution to our problem. And then there's the end. So when after this, it'll just do random junk. I'm not sure what the rest of that is actually. Yep. So that's the whole program, and that's a comparison between how the algorithm could be done and could be ran on a it would be a Siemens 300 or 400 PLC versus how the algorithm could be run on the architecture of the ARM processor. And yeah, thanks very much.